Chapter 2 is about atoms and elements. So to begin, we are going to talk about some theories. So the first one, we have the laws that led to the modern atomic theory. So the first one we want to talk about is the law of conservation of mass. So in the law of conservation of mass, it just basically says matter is neither be created or destroyed. So the total mass of my reactants will equal to the total mass of product. So if you had a reaction here, what you'll see is the mass of your reactants, which is sodium and chlorine over here, is going to add up to the mass of the product, which is sodium chloride. Now, the second law we want to talk about is the law of definite proportion, okay? Law of definite proportion says that basically a sample of a given compound, no matter where they're from or how you've made them, they will always have the same proportions. So in this case here, if you wanted to look at sodium chloride, which is table salt, the ratio of sodium chloride, no matter if you have 100 grams of it, or if you have 58.44 grams of it, it doesn't matter. Your ratio of the masses for chlorine to sodium is going to be 1.54. Okay? So that's the law of definite proportion. Now there's another law. We call it the law of multiple proportion. Law of multiple proportion by John Dalton basically says that if you have two different compounds, okay, like carbon dioxide and carbon monoxide, carbon dioxide will always have a ratio of oxygen double to the carbon, but carbon monoxide will always have a ratio of 1:1 of the carbon and oxygen. So in this case here, we can see that the oxygen for carbon dioxide is always going to be the double the amount for oxygen for carbon monoxide. So basically, if you take a look at it, it says mass of oxygen that combines with 1 gram of carbon dioxide is going to be 2.67 grams. And if you looked at it, whatever that combines with 1 gram in carbon monoxide is half of it, 1.33 grams. The ratio will always be 2 because you know there's 2 oxygens in 1 carbon dioxide and 1 oxygen in carbon monoxide. So they're just saying that's the law of multiple proportion. Okay, so these are all the laws that they've observed about chemical compounds. And then Dalton came with the atomic theory that was established. So his theory was that matter was based on something that's indivisible, a small unit that cannot be further broken apart. Each element is composed of tiny little particles called atoms. At that time, he thought atom was the smallest thing ever, and all atoms on the same element have the same mass, and they have distinguished, different properties, and that's different from other atoms of different elements. And then you can combine these atoms in simple and whole number ratios as these other laws that we've seen, multiple proportion and the other laws, it says, you can combine things in whole number ratios. So he's saying basically you can just take the atoms and rearrange them, and you can make new compounds, and you can count whole number ratios of atoms. Okay, so that's the beginning. We know that's not quite true. We'll come up with more discoveries here. So the first thing we want to talk about is they talked about the atom. They didn't know that the atom wasn't the smallest thing. There's actually little things in the atom. So they had to first discover the electrons after that, okay? So electrons, obviously we know is negative charge, and we know that for charges, if it's the same charge, they repel. If it's opposite charges, they're attracted to each other, okay? And then if you combine opposite charges, they neutralize. So in Cambridge, in a long, long time ago, J.J. Thomson had a cathode ray experiment, and he realized that he basically discovered electron from the cathode ray experiment. He realized that these this glass tube here, when he evacuated all the air, he pulled a vacuum on it and he turned the power on where it's a negative to a positive. He can see there's a ray coming out, and no matter what item he put for the metals in there, it would always just shine a ray in there. And this was the basis of discovery of electrons. So over here, he took the rays and went ahead and played with the electromagnetic fields. He could move the rays up or straight or down depending on electromagnetic fields. And based on this experiment here, he found the charge to mass ratio of the electron. So first he discovered electron from the cathode rays. He said because it's a negatively charged thing. But then he didn't really know much about it, so then he did an experiment to look at the charge to mass ratio and found out that the charge to mass ratio over here is basically a negative charge, or it's really negative charge coulombs per grams. And then it found out that the this item here, which he named the electron, is 2,000 times lighter than hydrogen. So it's way, 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 way smaller. Lighter than the smallest atom that they know of at that point. So that was definitely a cool discovery right there, okay? So the next experiment here is in Chicago, Millikan's oil drop experiment. So he basically had a chamber that had, he ionized it, I guess it's kind of like nuclear ionization radiation, okay? So over here, he can ionize oil droplets here, and then there's a positive charge plate and negative charge plate. So he can modify the charges on the plates here, so he can control the droplets once they're ionized, and the droplets can either free fall or they can actually float or kind of just dance up and down there. So based on this experiment here, he actually was able to measure the charge of an electron. Okay, so J.J. Thomson discovered electron using the cathode ray experiment, and then he found out the charge to mass ratio, and then Millikan in Chicago found out what the exact charge of the electron. Okay, so it's negative 1.6 times 10 to the minus 19 coulombs. And then from there, because they knew the ratio before that, they found out this is the mass of electron, which is super, super light, 9.10 times 10 to the minus 28 grams. Okay, so let's keep moving here. So we got the discovery of electron. So based on the discovery of electron, J.J. Thomson was the pioneer at that point. And since he was in England, they came out with the structure of the atom. Okay, so they were modifying based on what Dalton said, right? Dalton talked about how atoms are the smallest thing and all that. So over here, J.J. Thomson came up with the plum pudding model. So why the plum pudding? So if he was in America, he probably would call it a blueberry muffin model. Okay, it's kind of like a blueberry muffin. You want your blueberries all spread out evenly in your muffin. Okay, so plum pudding is like that. So this would be a blueberry, 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 and then that's your entire muffin right there. So he's saying that the electron is spread out all over, and then the overall sphere of the atom is a positive charge. That's how the atom is. And that was his model, okay? So in this case here, he was, basically establishing a new structure of the atom. So his student, Ernest Rutherford, is going to do an experiment later on to try to prove this theory, the plum pudding theory. So before that, there were already basically discovery of alpha particles, and they're going to use these alpha particles in a GoFol experiment. Okay, so Ernest Rutherford was, I guess he was the son of a farmer and I think a school teacher. He actually almost didn't get the scholarship to go study with J.J. Thomson in Cambridge. He actually was the runner-up. The student that got awarded at first decided he was just gonna stay home and get married. He gave up the scholarship, so Ernest Rutherford took the place. And he did great things with it. Okay, so he did an experiment here. This is a lot later years after he worked with when he first got the scholarship. This was a lot later. So he started this experiment here with his students at that time. He already became a professor. And then over here, they put an alpha particle source here. Okay, so alpha particle is going to be positively charged, and they're going to make it hit the gold foil, and they have detector all around it to see what the patterns would be. Now, what he was prepared to see look completely different than what he saw. Okay, so this was their hypothesis. Alpha particles would just pass straight through. Okay, if the plum pudding model was correct. But instead, what he saw was, instead of going straight through, some of them kind of went off sideways, and some of them almost got reflected backwards. Okay, so they were really shocked to see this discovery. He actually said it felt like you were shooting a bullet into a tissue paper, like soft, like Kleenex or whatever, and then the bullet, instead of going straight through, it turned around and came back at you. So that was a really big shock for them. Okay, so the only way to explain this, and actually took them quite a bit of time, probably a few years, to decide on why this would happen. Basically, you had to have a center in the middle of your atom, which is the nucleus. Now we already know that. So at that point, nobody knew what was in the nucleus. So he had to predict that there was a positive charge in the nucleus, okay? And then on the outside is where the electron cloud would be. And that's the only way when the alpha particle hits the positive charge, it turns backwards. And sometimes if it hits on the corner, it kind of gets moved around a little bit. And then the rest of the time it goes straight, okay? So he found out basically in the atom, we have a nucleus, and the nucleus has the mass of the entire atom. Because the electron weighs so little, it has no mass. The nucleus carries the mass of the atom. And the nucleus is also positively charged, okay? So these are things. So he essentially hinted at, so they basically knew the nucleus, because it was positive, there was protons in there, and then, and obviously to figure out the masses to make everything match together, there had to be something else that was neutrons. No, neutrons aren't officially discovered till maybe like a dozen years later. Chadwick found that out, discovered the neutron, okay? But Rutherford pretty much kind of got the clues to it. So that was the cool story about Rutherford. So he was actually just a runner-up student, but he took the scholarship and he made big things with it, okay? So that, now we know the breakdown of our atom. So in our atom, we know there's a nucleus. Inside the nucleus, there's protons and neutrons and an electron cloud around it, okay? Electrons are really, really light. So the mass, this is atomic mass unit, really small number, but if proton is weighed as 1 AMU, neutron is 1 AMU, electron is pretty much 0, okay? And the charge of a proton is positive, that's where the charges come from. Neutron has no charge, it's neutral. Electrons will be negative charge. So if you want to get the actual Coulomb charge is these numbers 10 to the minus 19 here, okay? As you can see, these are really, really light. All right, let's keep going. Why are these important? Well, every element on a periodic table is basically arranged by the number of protons it has, okay? The number of protons in the nucleus determine the identity of the element, okay? So the number of protons is also called the atomic number. And it's on a periodic table. So helium, if you look at a periodic table here, I'll show you a bigger version here. Like helium right there, okay? So this 2 over here, that's your atomic number. It tells you there's 2 protons in helium. Basically what they're looking up here. So this little chart here, the beryllium is 4. So beryllium is right here, it has 4. So this 4 means there's 4 atoms. So it's arranged, you can see the numbers are increasing on your periodic table in every box here. So this guy has 14 protons, which the atomic number is going to be 14. This one here has 26 protons. The atomic number is 26. So basically, that's how you can tell what the identity of the elements on the periodic table. The number itself, the number of protons, tells you what the element will be, okay? If it's got 23, it will be this guy. If it's got 12 protons, it will be this guy, okay? So let's keep going. Now, because we have protons that tell you the identities, the presence of neutrons and protons together gives you isotopes. So what in the world are isotopes? So isotopes are elements that are all with the same protons because they're chemically identical. So the number of protons are the same. So an example here is isotopes of neon. All of them have 10 protons. So if you look on your periodic table, neon here has 10. See that? So because it has 10, that means all of these guys have 10 protons. They will all be called neon. Now, under neon category, we have different isotopes, and each one of the isotopes has a little bit different count of neutrons. So one of them has 10 neutrons, one of them has 11, one of them has 12. So based on these two combination numbers here, atomic number is called number of protons, right? And there's another thing called mass number. Mass number is the addition of neutrons and protons together. So Z was atomic number, A is mass number. A will be addition of protons and neutrons together. So over here, when you want to write, sometimes you will say it's neon 20 or 2010 neon. Okay, you put the big number on the top, small number on the bottom, and then the big number means it's the total of protons and neutrons. Small number means it's just protons on the bottom right there. And then you can see there's neon 21, 2110, neon 22, 2210. And you can tell majority of the neon isotopes are actually in the 2010 form. And very little of it is the 2110. And about 9% of it is in 2210. So, you know, these isotopes are not always equal amount in abundance. One will be more prevalent than the others. Okay, so while we are talking about isotopes, remember isotopes are something that has the same number of protons, but a different number of neutrons, okay? So I want to go ahead and do a quick problem here on identifying isotopes. Okay, so in this case here, let me go ahead and write the question out for you. So I have a few things. We'll call them X's because we don't know what they are. So I have A, and another X, I have B, another X, this is C, another X, this is D. Okay, now I'm going to put you know, numbers on it. Big number, little number. Remember, big number is mass number. Little number on the bottom is atomic number. So mass number, in this case, this one's 35, this one's 17. Atomic number tells you the identity. Okay, now isotopes have same atomic number, but different mass numbers. Okay, so now this is A. Now this one here is B, 3518. And then I have 3617. And then I have 3519. And they ask you which ones are isotopes. Out of A, B, C, and D, can you see any one of these guys, or one, two of them, three of them, four of them are isotopes? And how can you identify isotopes? Remember, isotopes must have the same number of protons, different number of neutrons. So that means the same small number. The only choices you have here are only the ones with the 17 because they're the same protons. So the same protons, but different number of neutrons, giving them different mass numbers. That would mean A and C are your isotopes right here. Okay? So just wanted to make sure everyone understands that. So a lot of times, when you see it like a symbol with letters, it's easy to tell these are isotopes. But whenever you take out those symbols over there, you still have to remember which one is your isotope. Now, let's go ahead and go over some problems here. So it says here, the next question we want to work on, we want to focus on chlorine, okay? So right out. It says here, what is the atomic number which is Z, okay? And mass number, which is A, and symbol of chlorine isotope with 18 neutrons. Okay, so then if you wanted to do this problem here, we need to take a look at our periodic table. So go ahead and pull up a periodic table here. So you'll have to be able to tell which one is chlorine. So if you've seen this during your intro chemistry, this one here is chlorine. Okay, so chlorine here is Cl. We'll use the symbol Cl. And what's the number of proton? Is number of protons is 17 right there. So that means your Z atomic number is 17. And if you were to write it, it would be Cl as your symbol, 17 on the bottom, right? Now 17 on the bottom, and then it says the isotope has 18 neutrons. So that means you gotta take 17 plus 18 to get the mass number A that goes on the top right there. So in this case, 17 plus 18 would be 35. Okay, that's how you would write the symbol. Or sometimes they'll just call it Cl35. Okay, all right. So let's go ahead and look at another example right here. So the next one we want to talk about is 5224 Cr. Okay, and you need to find out how many protons, electrons, and neutrons are there in this atom. So if it's an atom that has no charge, so if it's no charge, your protons and neutrons will be the same number, okay? So that's the number of proton. Remember, Z is the number of proton. That's 24. And then you want to do okay, and then A is 52, and that's really protons plus neutrons. And we already knew how many protons there was. That was 24. So 52 equals to 24 plus the number of neutrons. So that means how many neutrons do we have? We take 52 minus 24. You get 28 neutrons. Okay, now because we said it was an atom, our number of electrons is also 24. Okay, all right, so while we're talking about an atom, we're saying, atoms are same number of protons and electrons. Let's go ahead and talk about ions a little bit, okay? So what kind of ions do we have? We have cations and anions. Cations are positively charged when you lose electrons, and anions are negatively charged when you gain electrons, okay? So basically, usually the anions are formed from nonmetals on the nonmetal side of the periodic table. So when you look at the periodic table, you have the nonmetal side And then on the this side here, this is your metal side. All these guys over here, they like to form anions. All these guys over here, they like to form cations. Positive charge here, negatively charged there, okay? So for example, it says, the way you want to name anions is anion, when you take fluorine, you want to turn it into anion, you call it, you take out the last letters here and you replace it with IDE. So fluorine will be fluoride, oxygen will be oxide, okay? And then they determine, oh yeah, this one you add 1 electron, this one you add 2 electrons. So we gotta decide, how do they know how many electrons they wanna put in or take out? But that's anion, okay? Now, if you had cations, cations are actually gonna be the same name. Sodium will be sodium ion, calcium will be calcium ion. So that's pretty simple. Now, when you want to form cation, it's because you're removing, you're losing electrons. So the electron is written out as a product over here. So you see sodium atom turns into sodium ion, cation, and an electron that was taken out. So you write this on the product side. Same for calcium. Calcium atom equals to calcium 2 plus charge ion, and then the 2 electrons that you took out. Okay, so we have a periodic table here. It says, Russian chemistry professor Mendeleev arranged it. He started putting it in, arranging by increasing atomic number. Okay, and then when you start putting them together into columns, we call them groups. So in this case here, we have groups. We can start talking a little bit about charges too. So we have metals, nonmetals, and metalloids. So these guys in the middle here, that's metalloid right there. Nonmetals, these are all metals over here, but this side over here is the main table, and then there's these guys here, these are your transition metals, okay? But there's metals, nonmetals, and in the middle, the metalloids. Now, metals and nonmetals, some metals are good conductors of heat and electricity. You can shape them into sheets, you can make them into wires. They're usually shiny. Metals tend to lose electrons. Non-metals don't really conduct heat or electricity, tend to gain electrons. Metalloids kind of are a mixed bag. Some are semiconductors, like silicon and germanium, okay? So let's talk a little bit about groups here. So on our periodic table, you'll see numbers on the top, okay? So you see how there's 1A, 2A, 3A, and then there's B's. So those are your groups here. So same thing, this will be the same periodic table you got during your exam. See how there's 1A, 2A, and 3A, 4A here? These here are because it's the transition metal groups, okay? So we want to talk about the main table elements for now. This is group 1, this is group 2, and this is group 3, 4, 5, 6, 7, 8, okay? Now, these are our main table groups, main group elements, and then in the middle here, the B ones are transition metals here. So going down is called group, and they kind of behave about the same, all in the same group. It's really cool. So we'll start talking about the different groups and different reasons why certain things have different charges. It'll make things easier once you put the whole picture together. Now, another thing you want to name is when you go from left to right, across the periodic table like that, this line here is a period. Okay, going down is a group, going to the right is a period. So the first period is H and HE, second period is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And then you have your third period here, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So that's the third period. And then you have your fourth period, and then you start seeing the transition metals in your fourth period. Okay, so this is important. We got to know periods go across the periodic table, groups go down a periodic table. Things in a group all kind of behave about the same. They're like a family. They all are related. They have similar features. okay? So let's talk about some groups here. They say group 8 are noble gases. Group 8 is helium, neon, argon, krypton, xenon, and radon. So all these down here, these are your noble gases. They're super, super stable. They don't need to react, so they're not reactive. Okay, they're very stable. And because they're very, very stable, everybody wants to be like that. They're noble. So kind of like, I guess, the royal family of the periodic table. Okay, everybody wants to be the king and queen or the princess, right? Princesses. So that's the noble gases right there. Now, group 1 is called the alkali metal. Alkali metal is right here, this group here. So hydrogen isn't part of it, okay? So it's lithium, sodium. Hydrogen is in group 1, but it's not technically a metal. So it's not a metal. So lithium is a metal right here. So lithium, sodium, potassium, rubidium, cesium, and francium. Okay, these are your group 1 metals, and they're going to be really, really reactive. Okay, why are they reactive? So it's kind of all has to do with group 8 here. Everybody wants to be like noble gas. They want to have, they want to look like noble gas. So you see here, they're actually trying to match the number of electrons. So neon has 10 electrons and 10 protons because it's neutral. Sodium has 11, right? So neon and then you have sodium. Sodium has 11, sodium is right after that. Sodium's like, well, I have 11 electrons. I wish I had 10 because 10 would be better because 10 is noble, okay? So, and then it's basically saying everybody wants to have the same electrons as the noble gas. So sodium wants to have 10. They're like, well, I have one too many. I'm going to give one away. So because sodium likes to give one away, it's very reactive at giving that one away because it's so close to perfection. It will give one electron away and it will always be +1 charge. And then potassium will be like, yeah, I'm 19. Well, argon has 18. I should just give one. I can be like, just like argon. Okay, so they're not going to change too much. They just change to the one that's closest to them. So potassium will lose one electron. Will be K plus cation, 1 + 1 charge. Same for all these guys below here. Okay, so group 1 will always turn into +1 charge, +1 cation. Now group 2 are called alkaline earth metals. They're reactive, but not as reactive as group 1. Okay, why? Because they are 2 away from perfection. This is magnesium has 12. It needs to have 10 electrons. It's like, well, I'm 2 away, so I guess I could remove one and remove another one. Then I can be just like neon. Okay, so it is going to be reactive, but not as reactive as group 1. So that's magnesium, calcium, beryllium, all these guys down here. And they will go ahead and lose 2 electrons. So the charges will be Mg2+, Ca2+, Sr2+, Ba2+, all will be 2+ charge. So kind of easy to remember. Group 1 + 1 charge, group 2 + 2 charge. These are going to make cations, okay? Group 7 are called halogens. So halogen is group 7 right here. Fluorine, chlorine, bromine, iodine, and astatine, okay? So they're very reactive nonmetals. Why are they very reactive? It's kind of like the same as group 1. They're super reactive because they're so close to perfection. Fluorine has 9 right here, and neon has 10. And then fluorine's like, well, I need just one more. So it's really, really hungry for electrons. It's like, I only need one more to be perfect. So anytime there's an electron nearby, fluorine will go ahead and steal it. Okay, it's very reactive at taking electrons. So it'll take 1 electron in, it will be -1 charge. Take 1 electron in, Cl will be negative charge, Br will be negative charge. You'll always just take 1 because you're 1 away from perfection. Basically the number of electrons that noble gases have. Okay? So that's how we can tell the charges of our ions, which is what they are showing here right now. Let me zoom in a little bit for you guys. So in this case here, you can see group 1 is going to be +1, group 2 is +2, and then group 7 is -1. Group 6 is 2 away, so it'll be -2. Group 5 is 3 away, -3. Once you get to 4, they're like, it's really too much effort, so they technically don't really form ions anymore. They instead of turning into ions, they go ahead and share the electrons. Instead of losing or gaining electrons, they share in covalent bonds that will make molecular compounds, okay? We'll talk about that later. Now, aluminum, though, is always fixed charge. It's going to be +3 because it's in group 3. Aluminum is like, well, I'm only 3 away. I can go ahead and lose 3 electrons. That can be aluminum +3. Okay? All right. So let's go ahead and talk about charges. So we talked about a charge that says aluminum is +3 because it's 3 away, right? So if you take a look, aluminum is 13. 13, the closest noble gas to 13 is 10. So I'll lose 3. Now the next one we want to talk about is sulfur. Okay, so sulfur is 16 electrons, 16 protons, 16 electrons as neutral atom. And then which one is it closest to? The closest noble gas is 18, so it's 2 away from perfection. So we will want to go ahead and gain 2 electrons to have 18 electrons to look like argon. So sulfur is going to turn into sulfide, S-U-L-F-I-D-E. Take the sulfur, change the UR, replace it with IDE. So you get sulfide is a -2 charge, okay? And then we can say if it's a nitrogen here, it will be nitride, N-I-T-R-I-D-E, and it will be -3 charge. So you can kind of, go all over the periodic table. But remember, pick the noble gas closest to it. And remembering that your nearest exit may be in front or behind you. So some of them will have to go backwards, kind of like remember for sodium, 11, you gotta look back, and 10 is closest, okay? The rest of them is kind of like, well, 16 is closest to 18. So you gotta keep that in mind. They always try to mimic the electron count of the noble gas that is closest to them. All right, now that we know about ions, we wanna talk about something else. So another thing that we haven't really talked about is we talked about the abundance of isotopes and how you can have isotopes. You have different number of neutrons, same number of protons, and we also talked about the abundance of each isotope I showed you for the neon one, right? So now what we want to focus on is actually how in the world do we calculate something called the atomic mass. So if you notice, we had mass number, we have atomic number, and then there's these numbers here. It's like, what is that? That's actually the weighted average, the average mass of an element. That's the atomic mass right there. Okay, so that's your number of protons. And that number here is the atomic mass. Okay, and if you have one atom of Cl, it will be an average of 35.45 atomic mass unit, AMU. All right, so let's talk about how we can get that. So they average this mass out. It's not like you have 3 samples, you add 3 up divided by 3. That's assuming if all of them have the same abundance. But we know that our isotopes are never the same abundance, okay? For example, if you had chlorine, chlorine has 2 isotopes, okay? There's a Cl35 and Cl37. So chlorine, Cl35, that means it's got, chlorine 17 protons, and then you have a certain amount of neutrons here. This one has a higher amount of neutrons. And then it says that chlorine 35, the mass of that guy is 34.97, and the mass for Cl37 is 36.97. But Cl35 is 76% of the time in occurrence. It's pretty common. And then Cl37 is only about 24% of the time. So it's not 50-50. So you couldn't take mass 1 and mass 2 and divide by 2. You can't do that. You have to take into account how often does it happen. So instead of our formula taking it and divide by 2 or adding all of them divided by the number, we go ahead and do a weighted formula, weighted average formula. So the first number is the fraction out of 1. So if it's 75% out of 1, you just turn it into fraction, okay? So 75.77 fraction out of 1 will be 0.7577. And then you multiply with the first mass right there. And then that's one term. You add it with the abundance of the second one and the mass of the second one. And if you have more isotopes, just keep going. Basically, every isotope you have, you take the abundance times the mass, and then add the next one, abundance times the mass, add the next one, abundance times the mass. And then when you add them all up together, you can get the average. So this here is the weighted average, okay? So let's go ahead and do a couple example problems here before we keep going. So I want to go ahead and write it out for you guys. All right, the first one we want to work on, we're going to talk about copper. Copper has two naturally occurring isotopes. Okay, we have Cu63 with a mass of 62.9396 AMU and abundance of 69.17%. Okay, that's the first one. And then you have copper 65. It has a mass of 64.9278 AMU. Okay, and they didn't tell you the abundance. You just left it blank. They didn't mention it actually. And it says calculate the average atomic mass of copper. So how in the world do you do this? And first of all, you'd be like, well, they didn't give me the abundance. How can I do that? I'm missing a number. Now remember, if they only have two isotopes, these two will add to 100%. Okay? You take 100% minus 69.17, you got the other percent. Agree? So this one here will be 30.83% if you calculate it from 100. So even though they don't tell you all the abundance, just remember, if you know there's only two and you know one of them, you take 100 minus the other one. Okay? If there's three of them, they have to give you two, and the last one you can subtract the difference out from 100. You can still get it. All right, so now that we have that, we can go ahead and calculate the abundance. So the formula, remember, is, so the average atomic mass is going to be abundance of 1, fraction out of 1, times the first mass, fraction out of 1, times the second mass. So it'll be 0.6917 times 62.9396 AMU, and then plus 0.3083, and then 64.9278 AMU. So what I like to do is put these numbers in a calculator, okay? And then hit plus, and then do these numbers in a calculator at the same time. I try not to round at all. I keep all my numbers in my calculator. So you have to get good at using parentheses in your calculator, okay? Now in this case here, you'll end up getting 63.552562 AMU. So I don't like to round anything because sometimes on our test, they give you a lot of decimal places and you want to be able to get the closest number without rounding until the end step, okay? So in this case, you typically, the answer choices would match how many AMUs and decimal places. So in this case here, they might give you an answer choice of 63.5526 AMU. Because in this case, you have to round up over there. Okay, so let me give you an example where you have multiple choices you want to pick from. Our exams are going to be in multiple choices. Okay, so So here's an example of a test question, basically. Let me zoom out a little bit more so we can see. All right, right here. So the next question, we want to talk about gallium, okay? So gallium has an average atomic mass of 69.723 AMU. So this is atomic mass unit right there. So let's give you some information. So that's the average atomic mass, and it say the gallium 69 isotope, the mass is 68.926 AMU, is 60.11% abundant. Okay, what is the AMU of the other isotope? Okay, so it's not like kind of like spelling out everything for you. They're asking you, what's the AMU of the other isotope? So if you first read this, you were like, okay, first of all, I know there's two isotopes, but then they only gave me information on one and asking me how I'm going to get it. So you got to remember, if I know the abundance of one isotope, I know there's two of them, the other one must be the difference between 100 and 60.11%. Okay, that's how you get the abundance of the second one. So I'll write down, assume there are only two isotopes. All right, so our answer choices, I'm gonna go ahead and show you what it looks like. 70.932 AMU, B, 70.920 AMU. So you see how close they are? You get in big trouble if you start rounding too early. 70.928 AMU, and D, 70.924 AMU. As you can see, they're all so close. Rounding would be so dangerous here. Okay, so let's go ahead and set up our formula. Formula is, I know that average, this is the outside answer, and that equals to abundance times mass plus another abundance times the mass, and we're looking for the second mass. I'm going to go ahead and set it up so you can see which part of it is missing. So 69.723 AMU equals to my first abundance, 0.6011 times 68.926 AMU. And then plus the second abundance, remember it is 100% minus 60.11%, you get 39.89%, okay? So I will go ahead and put down 0.3989. This one here, we get from 1 minus 0.6011, okay? In case you forgot that. And then the mass of the second isotope, which is what we're looking for. I'm just going to go ahead and call it X. So we're going to go ahead and solve for X here without rounding at any step. So you want to go ahead and keep everything in your calculator, do it all in one operation. Okay, I'm going to rearrange it with algebra. So basically, this will be one answer right there. And you can take the equation, basically it'll be 69.723 minus these two terms here, 0.6011 times 68.926. Okay, and then you have to divide by 0.3989. So this is just algebraically rearranging to get the X. Now, if you guys have trouble with this, make sure you reach out, let me know. I can try to help you, but there is also a dynamic study module and some hint and help with math on your online homework for extra credit. Dynamic study modules will be extra credit. So make sure you guys work on it to figure out how to work your math, okay? Now, in this case here, put it all straight in your calculator and you actually get 70.924 AMU. If you round it here and there, you might get a slightly different answer, and then you might get in trouble and get the wrong answer right there. So you want to make sure you try not to round at all, okay, until the end, whenever you have to stop. All right, so let's keep going. We will continue. So one way we can find out the amount of abundance of isotopes is by using mass spectrometry. So mass spec here, basically you shoot your sample in and they'll separate your samples according to your mass, how heavy things are. And like the more the stuff, the taller the peak will be basically. So if you shot your chlorine isotopes in there, you'll see that chlorine happens about 76% of the time, and then this one happens about 24% of the time. So, and you can kind of see it show up in peaks here. So mass spec is pretty cool to use for identifying isotopes. You actually use mass spec in organic chemistry a lot too. When you have a mixture of different compounds that you made, and you shoot it in the mass spec, it can tell you, okay, how much of this first compound do you have? This first compound weighs this much, the second compound weighs that much, and you have maybe more of the first one compared to the second. You can kind of tell what's in your samples, okay? Now, the next thing we want to talk about is about moles and molar mass. So we talked about atomic mass units. Say one atom of chlorine was 35.45 atomic mass unit. Remember we said that that's AMU right there. So one atom of oxygen is 16.00 atomic mass unit. So we want to relate them with moles. So how do we relate it? So 1 mole is like, instead of, the reason why they use 1 mole is 1 mole symbolizes 6.022 times 10 to the power 23, whatever you're talking about. Well, if you had 6.022 times 10 to the power 23 cookies, you'll be eating cookies for a long time, correct? So 1 mole cookies is a whole lot of cookies. 1 mole of eggs is a lot of eggs. One dozen of eggs is 12 eggs. So something like that. So why do we end up with this number though? It's because at that number, there's a cool connection. Over here it says 1 atom of chlorine is 35.45 AMU. 1 mole of chlorine is going to weigh 35.45 grams. So the mole, the number for mole, 6.022 times 10 to the power 23 number of chlorine is the connection between AMU and grams for the periodic table. Okay, and that's why instead of saying, well, it's 6.022 times 10 to the power 23 is a mouthful, they just call it a mole. And this number is the Avogadro's number. And the Avogadro's number will be on your periodic table as well as one for your symbols. So in case you do panic and you forget that number, it will be there for you, okay? So that's why we have this big number, is because we want to link what's on the periodic table saying 1 atom beryllium weighs 9.012 AMU, 1 mole beryllium, which is 1 times 6 which is 6.022 times 10 to the power 23 atoms of beryllium will weigh 9.012 grams, okay? So we will be talking about that. We'll do some math, but I wanted to show you over here. So they're saying, see how that's the Avogadro's number? Because that's a link between AMU and grams, okay? So then they show you all these examples here. 1 atom of hydrogen is this, 1 mole of hydrogen is this many grams. This is the same exact thing, but the relationship, the link is this here, the Avogadro's number, which is in 1 mole. That's the link between AMU and grams. Okay, so now that we have this information, we can probably go ahead and try to do some calculations of conversions between grams, moles, AMU, atoms, and all that kind of good stuff. And that after these problems will be the end of chapter 2. So let's go ahead and get to it. Now, the first one we want to talk about, an example is this one. Calculate the number of copper atoms and 2.45 moles of copper. So if 2.45 moles of copper, how many atoms are there? Remember, 1 mole has 6.022 times 10 to the power 23 things. So we're speaking atoms here, okay? So we say if you have 2.45 moles of copper, I want to turn it into atoms. And I will have to make sure I cancel out moles on the top. Okay, so 1 mole is 6.022 times 10 to the power 23, right there. So when you have this bridge here, you can put this either on the top or bottom, this on the top or bottom, you just wherever it's convenient. I'm trying to cancel all the moles, so I put the moles on the bottom. Okay, so in the end, you can see that you really just take the moles times the Avogadro's number right there, and you'll get your answer for your atoms. In this case, my answer will be in 3 sig figs here because this one has 4, this one has 3. I'll keep 3 sig figs, so 1.48 times 10 to the power 24 copper atoms. Okay, this is the Avogadro's number on your periodic table or in the simple Na on your periodic table. That's that number right there. Okay, all right, let's do another conversion. The next one is convert 1.1 times 10 to the power 22 silver atoms to moles of silver. So the formula for silver is Ag. So 1.1 times 10 to the power 22 Ag atoms. You want to convert it to moles of Ag. So you want to put the atoms on the bottom. So it's 1 mole is 6.022 times 10 to the power 23. So that means in this case, you want to go ahead and divide that value. You want to make sure you know how to put this in your calculator correctly, okay? And if you have trouble, make sure you get help. When you put these numbers, this one divided by that, you should be able to get this in your calculator. A lot of times, if you don't try it on your calculator, you don't realize you're not putting in the numbers correctly. So I want to make sure you guys are using, number one, the correct calculator. You cannot use this programmable calculator. So TI-83, TI-84, all those basically fancy, expensive calculators, you will not be able to use it for our class. It will be checked during exams. So you want to make sure and go ahead and get the correct calculator for our class. You want to get a scientific calculator. I prefer a dual line display so you can see what you type in. It should be about like max, you want to spend $15 on it. It's not an expensive one. Make sure you get the correct one. It will be posted on class, and I'll like announce it in class as well. Okay? Check your My Courses and syllabus. All right. So in this case here, you divide it, and you should be able to keep 2 sig figs in your answer. So I will get 1.8 times 10 to the minus 2 moles of Ag. Okay, I just want to make sure you guys are aware and you know how to put this in your calculator. Make sure you take out your calculator and practice this right now, just to make sure you know how to do it. If you know how to do it, you're good. If you don't know, make sure you get help ASAP. All right, let's go to the next problem. Calculate the amount of carbon in moles contained in a 0.0265 grams pencil lead. We gotta assume pencil lead is pure carbon. Okay, so it's just basically carbon. So if you have 0.0265 grams of carbon, they want you to change it to moles of carbon. So you gotta change it to moles of carbon. How know where are you gonna do that? Well, look on the periodic table. On our periodic table here, carbon is 12.01. So 1 mole of carbon is 12.01 grams. Okay, so then I know, oh, look, my mole goes on the top. Remember, MOL is the abbreviation for mole, not M. Okay, M is for meter, mole. So 1 mole of carbon is to 12.01 grams of carbon. And I put the grams at the bottom because I want to cancel these guys off. So then my answer will be take 0.0265 divided by 12.01. I'm going to be able to keep 3 sig figs here, okay? Because this is 3 sig figs. So my answer will be 2.21 times 10 to the minus 3 moles of carbon. So hopefully everyone is able to get that. Make sure you try this out with your calculator. While we're doing these problems, it's always a good thing first to watch them, write it out together, and then later on do these problems again without help. So like write the question out, leave the work part blank, and try to see if you can do it on your own. If you still have trouble doing it, then you need help, okay? Try to sit there until you can figure it out. Watch the videos again if you need to. But if you still have trouble, always make sure you get help. All right, let's go ahead and do one more problem. The last problem before we end our chapter. Okay, so let's go ahead and write out. So this one says how many copper atoms are in a copper penny with a mass of 3.10 grams. Assume penny is pure copper. You know, copper nowadays, the newer ones aren't pure copper anymore, but they're older ones. I can't remember 1980 something. I think before that year, they're all pure copper. So we actually found one in class and lab. One of my students had it. And we actually weighed the copper penny, and it's actually pretty darn close to 3.10 grams. So that's pretty cool. So maybe look around at home, see if you got an old copper penny. Try to weigh it out in your kitchen balance and see if you got about the same number right there. And then you can tell them, hey, you know what? I can calculate the copper atoms in this penny for you. All right, so we're gonna go ahead and do this problem. So based on this, if it's copper, it's gonna be Cu. So Cu is gonna be 29 atoms, right? That's your number of protons right here, and the mass number will depend on how many neutrons, but this is the average mass. So it's 63.55 grams per 1 mole of copper. Okay, so I'm gonna go ahead and write it out. 1 mole of copper is 63.55 grams of copper. And then they also want you to find out atoms. Remember, 1 mole atoms and 1 mole copper has how many atoms? 6.022 times 10 to the power 23 atoms of copper, because that's the Avogadro's number right there. So that equals that, that equals that. So what we're going to go ahead and use is this connection right here, right? We got these two pieces together. So I say I have 3.10 grams of copper, and I want to turn it into atoms. So I'll put the atoms number on the top. So it's 6.022 times 10 to the power 23. And then I want to cancel the grams in the bottom. So grams of copper goes here. It's 63.55 grams right there. Okay? So when you put this in your calculator, you take 3.10 times 6.022 times 10 to the power 23 divided by 6.022 63.55, and then you should get your answer. Now, how many sig figs do we want to keep in this answer? We only keep 3 because these guys all have 4 sig figs, but we only want to keep the smallest, so we keep 3 sig figs. So your answer should come out to be 2.94 times 10 to the power 22 copper atoms. All right, so that should be what we want to cover for chapter 2, and I will see you guys for chapter 3. Make sure to go over these problems again, try to work them out. If you don't know how, try to get help ASAP.